Circular motion. So 63, problem 63 is a pretty good representation of what you'll need for circular motion. It is about a purse at radius 2 meters and a wallet at radius 3 meters on a merry-go-round. So don't need anything fancy for a drawing. Just a couple circles. And here's the purse. Here's the wallet. It's 2 meters from the center to the purse, 3 meters from the center to the wallet. Guess I'll stick the 3 here. It's for the whole length. So, what do we need to find here? We need to find what's the acceleration of the wallet if the acceleration of the purse is, so let's just write that down. The acceleration of the purse is 2 meters per second squared in the x direction and 4 meters per second squared in the y direction. Well, first off, we need a couple things. Circular motion deals with motion in a circle, and uniform circular motion, even more so, is when you're moving around in the circle at a constant speed. Not velocity, because your direction is always changing, right? But your speed is the same. In other words, it's like playing a record or something, or driving at a constant speed. The turn rate is not changing. So when that happens, there's no what they call tangential acceleration, meaning acceleration like speeding up along this line. Because you could take a circle, right, and like just like a roll of like a fruit roll up, and just flatten it out. So what used to be circular is now linear. So here's one end of your circle. Like here's a point on the circle, right? You cut it, flatten it out, and then these two endpoints used to be touching together at this point. So anyway, moving around the circle is the same as moving along this line. So if you're speeding up along the line, if you start at rest and you go and speed up, end up at like 10 meters per second here, you've accelerated along the line. That's called tangential acceleration because you're always tangent to the circle, right? Your acceleration is, if you're moving this way and you're speeding up that way, then your acceleration is at this moment up here, that way. At this moment, down. This moment, over. But uniform circular motion, there is no acceleration tangentially. All the acceleration is pointing towards the center radially, because your velocity is changing. You may not be speeding up or slowing down as you go around, but your direction is changing. And if either of those are changing, you are accelerating. So we call that centripetal acceleration, and that happens to point towards the center of the circle. And it has a magnitude v squared over r, where v is your speed around the circle, and if it's uniform, the v is not changing, and r is the radius. So you need that. You also need the length of this line, in other words, the circumference of the circle. Circumference equals 2 pi r, right? So your velocity around this, if you're going at a constant velocity, v is your distance traveled around the circle, which is your circumference over your time. So that's 2 pi r over your time. These are all, I'm basically just introducing the circular motion equations. I think I actually probably introduced these in the unit videos. I don't remember. Let me go check. I'll be right back. I'm back. Well, sorry about that. I think I wasted about 4 minutes of your life reviewing that. And you probably just watched that video, well, if you're going in order, maybe like a few hours ago or maybe a couple days ago. But anyway, yeah. So this V can go in here, as you know, and A centripetal can be 2 pi r squared over t squared r, which simplifies to 4 pi squared r. This r cancels with one of these two r's over t squared. Why did I do that? One sec. Yeah, so that's fine. So now we can compare. We know that essentially what is the same for both of these, as long as they don't slip around on the merry-go-round, is the time to go around is the same. But that makes motion out here more difficult because you got to cover a longer distance, a bigger circumference in the same amount of time. So you got to actually be moving faster, right? But the time is the same. So if we solve this for time here, this becomes time equals the square root of 4 pi squared r over a centripetal. But the time for the wallet equals the time for the purse. So essentially, the square root of 4 pi r of the wallet over, squared over acceleration centripetal of the wallet equals the square root of 4 pi squared r of the purse over a of the purse centripetal. The squares and square roots and the 4 pi squares cancel, so this turns into essentially r wallet over a centripetal wallet. Sorry, I'm just mixing up my letters. Equals r of the purse over a centripetal of the purse. And we know the radius of each of these. So the wallet is out at what, 3? Yeah, the wallet's out at 3. So this becomes, let's just do this over here, 3 over a centripetal wallet equals 2 over a centripetal purse. By the way, we're trying to find the acceleration of the wallet. They gave us the acceleration of the purse. The thing is, they gave it to us in component form. So over here, let's turn this into just the actual centripetal acceleration. And what is that? Well, we got 2 in the x direction, positive 2, 4 in the y direction, positive y direction. So that happens to be, the actual acceleration is that. So a is the square root of 2 squared plus 4 squared, which equals 4.47 meters per second squared. Right? And that's at an angle. We'll use this angle here. It's kind of messy, isn't it? I should put the 2 here. Make this the angle. Oh, that's much better. Much better. Not. Alright, so the angle is tan -1 of opposite 4 over adjacent 2. And that gives us an angle of 63.43 degrees. So first off, we know that the acceleration angle is the same for both because they're along the same line. So, you know, this is 64 right here, 63.4 for the purse. It's also for the wallet. It's the acceleration that's not quite the same. So but we'll use this angle to break it back up into I and j components because the problem's asking for in unit vector notation, so we got to put it back into here. You could probably actually, if you're looking at this, see what it's going to be. For every 2 of the purse, you have 3 of the wallet. So for every 2 of the purse here, which there's 2, you got 3. So you can probably guess that the x component is going to be 3. And then for every 2 of these, you have 3. So double that, you get 4. Double 3, you get 6. So you might have already seen that, but we can just do it formally, and you'll be like, oh, it works out, cool. We got 3 over 4.47 equals 2. Sorry, we're looking for the wallet. Let's just back up a little bit. ACW equals 2 over 4.47. So A centripetal of the wallet is 6.71 meters per second squared. So that's like the hypotenuse. So we can break that up into components by doing cosine and sine. I'll actually, just to save some time here, either let you do that or you can trust me that 6.71 cosine of 63.43 is exactly 3, and 6.71 sine of 63.43 is exactly 6. Try it out. Okay, so that was a circular motion problem, and that pretty much has everything, all the circular motion main concepts that we need in it, including centripetal acceleration, circumference, velocity. So 2 more problems to go, and those are 1D motion relative velocity and then a 2D motion relative velocity. 2D motion ones are tricky, so you'll get it. Okay, bye-bye.